check. Okay, welcome to the 11th class meeting. As we canceled last class meeting on Monday, I'm still recovering from my... Okay, so last time I verbally explained something very interesting. And today I'm going to give you a more mathematical or close to mathematical point of view, why that kind of strange thing happens. That I named multi-stream decomposition. Whenever you have a phrase that is equivalent to a noun, usually you have some of and something that is described by this one. So multi-stream decomposition of what? And here goes the key when you remember this terminology, multi-stream decomposition of PAM or QAM signal. So whenever you see a PAM or QAM signal, you can apply multi-stream decomposition to understand what appears to be very strange. And that something strange is what? In this paper, shown in figure 4, as I described or verbally explained the interesting result last time. So think about a signal that is some A times summation d sub n p of t minus nt. So here, usually, if p of n is real valued, then this signal is called PAM. And if d sub n is complex valued, this signal is called QAM. So nothing different between PAM and QAM. Now, let me ask you, what is the symbol transmission rate of this signal if d sub n is the nth symbol? Obviously, every capital T you transmit or you send new symbol. So the symbol transmission rate 1 over T, and the unit is symbols per sec. And everybody will agree with this, with you when you claim this one. Multi-stream decomposition is a little bit weird, and it does something like this. So the first decomposition is this one. You consider even terms and odd terms. Now, you still have the same signal, but now you have two PAM or QAM signals as written here. And sorry about that, 2M. So what is the symbol transmission rate of the first component? the symbol transmission rate is now 1 over 2t. What about this term? Again, symbol transmission rate is 1 over 2t. Now, can you decompose it into 3 PAM or QAM signals? Yes, that's not that difficult. You may do something like this if you wish. Okay? It's your preference whether you subtract or add. It doesn't matter. If you want to be more consistent, probably I'd better use plus uh, signs instead of minus signs. In that case, see that here, from here to there, if you change this 3 to 2 and this upper limit to 1, then you can easily see that this one is same as that one. Now, what is the symbol transmission rate of each component? The symbol transmission rate is 1/3. Now you have 3 PAM or QAM signals. Let me draw a figure that gives you a better idea. Suppose we have BPSK signal. So this is T, 2T, 3T, 4T, and you have decomposition into 2 BPSK signals. Now, how many BPSK signals do you have? You have 2 signals. And what is the symbol transmission rate of each BPSK signal? 1 over 2T. Got it? So a single BPSK signal can be viewed as 2 BPSK signals. The difference is that here you look this one as a symbol rate 1 over capital T. And here you look each BPSK signal having symbol transmission rate 1 over 2 capital T. Got it? So in this way, you can decompose a single PAM or QAM signal into as many multiple streams as possible. Got it? Now, we need a little bit of leap of faith. So let's take a look at this figure again. So given the same signal of legacy, you are going to design your overlay signal. And here, on this curve, what is your point of view? You view the legacy signal as a single PAM or QAM signal, in this case, QAM signal. So you have a single, for example, single QAM signal, but probably not single in this case. Probably in this case, okay, yeah, it's correct. Single legacy signal. So you view it as a single legacy signal with symbol transmission rate 1 over T0. Now you try to do your best in designing the transmit waveform and receive waveform so that you keep complete orthogonalization at the output of the legacy A to D converter or matched filter. And you want to minimize the mean squared error to the overlay receiver. So here, how many stream do you have? You have one legacy stream with symbol rate 1 over T0. Now, what about this one? You have two legacy streams with symbol rate 1 over 2T0. You have 4, 8. Now, what is the kind of dimension or dimension you can exploit in the design of the transmit and receive waveform? Our intuition says that dimension depends on our symbol rate we choose. So suppose originally you had legacy signal with some roll-up factor or excess bandwidth. In that case, with respect to 1 over 2t, what is your dimension? So this is the bandwidth in passband, right? And if you choose the symbol transmission rate, then it would be very intuitive to divide the entire bandwidth in passband using the symbol rate. So 1 plus beta 2 to T0 divided by 1 over T0 is obviously 1 plus beta. And you may say, why? But if you remember how we designed our vectorized Fourier transform, you may have some feeling. Now, you have 1 plus some positive number. Now, what is your legacy signal's subspace dimension? And from your first exam, you derived and have found the legacy signal has rank what? At most 1 for every offset f for the vectorized Fourier transform. So here, dimension 1 occupied, actually it depends on your offset. Sometimes it's 2, but simply put, one dimension is occupied by the legacy. Now you have only beta dimension to design some signal that is orthogonal in some sense to the legacy signal. Got it? Now, given the same legacy signal, you choose 1 over 2T0 as your reference rate, then what is the dimension? Still the numerator is the same, but now you have denominator that held. Now, how many dimension is occupied by the legacy signal? At most 2. So 2 dimension is occupied by the legacy, and you have 2 beta dimension to design the legacy signal. Now consider 1 over 40. In that case, obviously, you have this one. And 4 dimension is occupied by the legacy, and 4 beta dimension is to be utilized in your design. And 8, you have 8 plus 8 beta, 8 dimension occupied by the legacy, and 8 beta can be utilized by the overlay. And here we assumed in our figure 4, the roll-off factor of the square root raised cosine pulse, which is the pulse of the legacy signal, equals the excess bandwidth in this case. So beta is gamma, and that is 0.22. So here, 0.22, 0.44, now what? 88, and 1 point what? Again, 76. Am I right? Right? So suddenly, from this choice of symbol rate 1/4T0 to 1/8T0, you have what? The dimension for the design of your overlay signal becomes greater than 1. Of course, you can choose 5T0, 6T0, 7T0, and which one will give you the first? Probably 5T0, right? So precisely speaking, from the transition 1/4T0 to 1/5T0, we have sudden kind of phase change occurs in H2O. Sometimes it's a gas, sometimes it's a solid, sometimes it's a liquid. Similarly, you have sudden change in the behavior of the system. So here, if you have 0.22, which is what? Which is, let's see, which 0.3, yeah, probably around here, right? So A has gamma equals 0.22, and that corresponds to this dotted line. And here you have a very poor bit error rate for probably, I remember, QPSK, even in a very high SNR, if I remember. Yeah. Let's find out what was the SNR. Okay, what is the SNR? Yeah, I don't remember. Yeah. But anyway, due to self-interference that is unavoidable, the overlay system suffers from interference. Why it is so? Because for each design up to this point, your bandwidth is less than the Nyquist minimum bandwidth that is required for you to design zero ISI signal. Got it? But here, you can design a zero ISI signal. That's why you achieve AWGN bound. Got it? So even though this paper, as far as I remember, but never believe my memory, I'm kind of getting very old. As far as I remember, I didn't mention any multi-stream decomposition here. And even I do not remember I mentioned that terminology in any of the research papers published from our group. However, we talked about it in more than a few patents written with myself and one of your former graduates. Anyway, so it's very, very, very interesting. And probably you remember there has been many projects announced by the 통신신호연구회 Communication and Signal Processing research group in Korea Information and Communication Society. They had the project like identifying number of PAM or QAM signals. And whenever I saw that, I didn't feel very well. The first one is that mathematically speaking, given a single PAM or QAM signal, you can say that you have 52 million PAM or QAM signals, if you want to say that. Okay? If you want. So finding out how many signals are in your frequency band of interest is a very hard problem if you just look at the signal after transforming it into some finite dimensional space and try to find the rank of your received signal, then you fail. Of course, you may say that, what if I choose some transmission rate and count the subspace dimension occupied by the interference over some signal, and then I double the symbol rate and recalculate, and if the subspace dimension halves, then you may say that, okay, it seems that the number of signals is not the number of subspace dimension originally I calculated. And you do it again. Or you choose the tripled symbol duration, or symbol transmission rate, and you count the number of subspace dimension. And that might work. But anyway, just try to find guess the symbol rate and try to figuring out the number of signals, PAM, QAM signals, is a very dangerous task, and you may easily fail. Now, you may say that, well, then what kind of strange signal there can be existing? And here goes another one. So usually when you talk about PAM or QAM signals, what is our kind of common sense? As I told you, we have a single transmit pulse. But is it necessary? What if some strange one what about this type of signal? So here, I intentionally have chosen 4 multiple streams, actually, with possibly different symbol waveform. So we have P0, P1, P2, and P3. And each one is going to be used in a round-robin fashion for transmitting D0, D1, D2, D3, D4, D5, D6, D7, dot, dot, dot. And you are going to use symbol rate 4t, 1 over 4t. Now, is x tilde t a single PAM or QAM signal or 4 PAM or QAM signal? Actually, it depends how you define PAM or QAM signal. But common sense is that as far as you have the same pulse, single pulse, repeatedly used, then you have a single PAM QAM signal. So here, it appears that you have 4 PAM or QAM signals according to the conventional or kind of common sense definition. But before defining or agreeing on what is the PAM or QAM signal, the answer could be anything, right? You may even view this as two QAM signals. And here goes another challenge. Since many of you are my research assistants, you know that given a square palm symbol constellation, you can decompose it anytime into multiple BPSK signals. BPSK symbols, for example, let's consider QPSK case. And each one could be Dn. Now, Dn equals what? Bin plus J in BQN. Here, B is either +1 or -1. Now, your QPSK signal can be rewritten as what? Now, let me ask you. According to our common sense, here the first PAM signal has symbol waveform PT. And the second term has J times P of T as the symbol waveform, which is different from Q of T. So sorry, let's say that this is Q of T. Right? Now, how many PAM or QAM signals do you have here? How many? Two? Two BPSK signals or one QPSK signal? And you may say that, well, professor, if A tilde is different from A, we may say that we have two BPSK signals. However, if A tilde equals A, we have one QPSK signal. You really want to say that. But mathematically speaking, it's very proper to claim that we have two BPSK signals instead of one QPSK signal. This can be repeated forever, actually. Let's consider 16 QAM. And this 16 QAM signal symbol, D sub n, can be decomposed into two 4 PAM symbols. Right? And each 4 PAM symbol, B, can also be decomposed into two BPSK signals with a different scaling factor. Because if you add either 2 or negative 2 and negative 1 or 1, you will have this 4 PAM symbol. Now, how many signals do you have? How many PAM or QAM signals do you have? Everyone is correct and everyone is wrong, depending on your definition of PAM or QAM. What really matters would be, to some people, would be subspace dimension. The problem is that the subspace dimension also is only relative to your choice of symbol transmission rate, right? So there are two things. One is due to the decomposition of symbol, especially modern square QAM symbol. Second one is what? You choose the symbol transmission rate and multiply number of streams. Got it? So there are two types of decomposition. Got it? So any answer which is consistent with that multiplications is correct. And any answer could be wrong depending on the definition of number of the definition of the PAM and QAM signals. Got it? So this is the first story. And that is the second story. Got it? By the way, as many of you already do the project, actually, this decomposition of symbol constellation can be done in very, very many different cases. For example, only the real part is decomposed into two BPSK symbols. And the imaginary can be viewed as 4 PAM. Or you may view you have two BPSK and two BPSK in the real and imaginary. Or what you can do is that you have one QPSK and another QPSK to make the 16 QAM constellation. And these two QPSK constellations have different scaling factor. Got it? You choose BPSK for the real, a smaller BPSK of the real, and smaller QPSK of the BPSK of the imaginary, then you have smaller QPSK. You choose bigger BPSK in the real and bigger BPSK in the imaginary, you have bigger QPSK. So in that way, you have two QPSK signals here with different scale. Now, you can easily see that the previous claim saying that if we have different scale, then you must count as different signals. You can't do that, right? Because in that case, how many signals do you have for 16 QAM? 2 QPSK signals? And still, some people may complain that, hey, we have same P of T in that case. But still, there could be any way, because it's like you can rotate the constellation, as many of you already know, pi over 2 BPSK or something. In that case, we can show that these two QPSK signals has different waveform. Again, some of your friends say that, okay, but however, that rank 1 matrix is the same, something like that in that case. And that is correct, actually. However, if you decompose the QAM symbol into PAM, especially pi over 2 PAM symbols, in that case, it's very, very complicated thing. I'm not going to talk too much about this one, but I believe you got the point. So let's go back to our optimization problem. The problem is almost the same as our 2004 paper, except that we have what? We have this B Hermitian transpose S equals 0. And as all of you spend some time in your during the first exam which was take home, you now understand how can you remove this equality constraints. Actually, how many? Because this is a vector 0. If you consider scalar 0 equalities, you may have more than one, right? In that case, you introduce the orthogonal projection matrix and just delete this one and plug in orthogonal projection matrices. Then you have the same, mathematically, the same problem as in 2004. However, what's the difference? Here, this problem already assumes you have chosen your reference symbol transmission rate. You have freedom to choose the symbol transmission rate for the entire optimization problem. That's why you have different solutions. Of course, in this special case, the spectrum, the power spectrum of your overlay signal is the same. And that also gives you an idea. Power spectral density is a very useful metric to see what kind of frequency content the signal has. However, it is not fully characterizing the spectral correlation. As you've seen already, given some autocorrelation function of a random process, usually that autocorrelation function is not what? Is not a function of time difference. So you have two variable autocorrelation function that fully characterizes two samples taken in the time domain from a single random process, if you want to consider autocorrelation. Now, this time domain correlation can be represented in the frequency domain by doing double Fourier transform or symplectic Fourier transform. In that case, you have two dimension, xi1 axis and xi2 axis, and you have some complex valued function that completely characterizes the spectral domain correlation over random process. And that is the key to understand cyclostationary random process, which is a very, very special spectrally correlated random process. There are other types of random processes that exhibit spectral correlation. And actually, this double Fourier transform, even though it fully characterizes the spectral correlation, it is not, how to say it is not give, it does not give you a clear idea in many cases, as if your Fourier transform over finite energy signal, as far as you have finite energy signal, Fourier transform contains all the information of your signal. However, why in audio signal processing why we use short time Fourier transform? Because this Fourier transform, which can be plotted as real part and imaginary part, or magnitude and phase, sometimes does not give us what kind of frequency content is concentrated at a specific time. It's very hard to see from the Fourier transform. Same thing happens. So let me first emphasize the importance of the two-dimensional or bispectrum over random process. However, as the second, you must be very careful in using that one. For cyclostationary random process, because of some periodicity in the up to second order moment, it would be very, very useful. Especially if you just vectorize Fourier transform the original signal. So you convert the original signal to a vector valued signal, then what do you have? As you've seen throughout this course, it becomes vector Y-sense stationary process. So this vector Y-sense stationary process's spectral correlation is 0 as far as you choose two different frequencies, right? So it is called stationarization. So whenever you have non-stationary random process, some pre-processing may, not always, may generate a random process that is kind of, that transform is invertible, must be invertible, and you have what? You have stationary random process. Then, as far as you have stationarity, then what you need is ordinary power spectral density. Got it? So far, we haven't yet seen other types of spectrally correlated random processes than the cyclostationary random process. So you may have some prejudice on spectrally correlated random process. That's why I'm kind of emphasizing the importance, so strengths and weakness of the vectorization and stationarization. Sometimes you cannot stationarize a non-stationary random process. In that case, even though mathematical bispectrum may contain all the correlation, it may not be that useful when you look at that. Got it? Anyway, so I'm not going to deal with all the details in this paper, but you know what I mean. Got it? By the way, you may have some question about what is this B matrix appearing in our optimization problem. And here is the B matrix Hermitian transpose. And as you see, actually, it is all related with the sampled output at the case. Case receiver with else sample output. Got it? So depending on your number of legacy signals, number of legacy receivers with the same sampling rate as your chosen symbol rate, you may have different number of rows here. So be careful. Got it? Anyway, so interestingly, this paper becomes the same mathematical problem as 2004 paper. However, the implication is quite different. Whatever small bandwidth you have, actually, you can squeeze your desired signal into the signal, legacy signal, and exploit that one as far as mathematically it is possible. And many of you may wonder why this very unrealistic scenario is considered. But as I once emphasized, when I was a graduate student, my advisor rarely asked to do something. He asked only twice. Once, he asked to process the data delivered from Raytheon, Dallas, and that was related to our biggest project. And I still remember that UPS package arrived in the table of our RA office. My professor brought it. Hey guys, we have the box from Raytheon. You know what to do. And it was put on the table. And in a week, no one touched it. And I was shimmering. Can you do that? Something like that. And eventually, I took it, opened, and started to read the data. And that became my task. That was the first thing. So precisely speaking, my advisor never asked me to do it. And second one is really my advisor asked. My advisor at that time, I remember Motorola, Schaumburg, they had the U.S. State or Illinois or I don't know, government has some interesting tax law saying that, for example, Motorola, they may have very, very expensive equipments, outdated, according to their standard. However, some of the equipments, measurement equipments, are very, very up to date for the researchers in graduate school. So my advisor asked the Motorola guys to donate those very expensive equipments. And they agreed because the tax law says that in that case, they can have some tax exemption depending on the donation. I think that is a very good tax law every nation should adopt. Anyway, so suddenly we have very, very nice satellite dish, very big, around 3 meters wide, very large. A crane was used to put on the top of the MSE building, and cable was installed to our second lab. There was a corridor between two labs, and there was a rack and a lot of equipments, automated something. So it's like we could monitor a lot of satellite signals and just push and dial and choose the band. The equipment automatically show the constellation and the spectrum, something like that. And from that time, I wondered why these guys in the field want to find out number of PAM and QAM signals, right? They wanted to automatize the display. Anyway, and suddenly my advisor had this idea. He saw some spectrum band And that was occupied by definitely a square root raised cosine pulse with Rho factor 1. We found one of the signal. And we plotted in the linear scale, and it was perfect raised cosine power spectrum. So we could guess that in the complex baseband, the spectrum looks like this. And suddenly my professor said that, hey, could we put one more signal here? Because satellite spectrum is very, very expensive. And we may show that if we can squeeze in one more signal in this band, which is already occupied, it could be a big money. And he asked me and another RA to do something, some simplified version of it. And that was like this. So suppose you have a BPSK signal with the symbol transmission rate T. Now, in the frequency domain, you have what? You have sinc square, right? So ideally speaking, you have infinite bandwidth. Of course, you don't have infinite bandwidth, so you have finite bandwidth, but in order to make everything simpler, let's consider this one. And let me ask you another question. What if you just put one more BPSK signal with offset half T? So your symbol rate is the same, but you just put one more signal. And he asked us to redesign the receiver given the signal model and compute the mean squared error at the output of linear MMSE receiver. And interestingly, the performance of the linear MMSE receiver for this one and that one didn't show much degradation. Why? Of course, we assumed matched filter receiver from the beginning at the first time. So matched filter output would be what? As you know, it's a triangular pulse, right? So this one becomes that one, right? And this one becomes that one. And one interesting thing is that, what about this part? At the output of the first receiver, it becomes something like this. So at the sampling instant, it gives you interference as far as the power is the same. Interference, that is just what? Half magnitude of the desired sample, right? So as far as the signal is BPSK and SNR is very high, performance is amazing. Then we try to change the receiver to a linear MMSE receiver, which is the best linear receiver in minimizing the mean squared error or maximizing the signal to interference plus noise ratio. So our performance further improved, especially in high SNR, right? And we were very, very excited. And the next step would be designing a band-limited signal and putting some band-limited signals, overlay signals. And at that time, I made a serious mistake, which was my if I count the top 5 disaster in my career, it would be the third one or fourth one. So at that time, my advisor was highly motivated to start a startup company. Even he registered the company, and it was a River Valley Wireless. And he purchased a lot of equipments motivated by the amazing results. The problem was that I published enough number of papers, and I started to have job interviews in the universities. And at that time, again, my advisor never asked me to stay for a while to assist his startup to startup. He never asked me. And now I'm really regret. I should have stayed there for more than a year uh, to help him and have some experience. Anyway, so I got a job. I left the lab. And unfortunately, when I visited the lab in yeah, 8 years, 8 years, before I had my first sabbatical at my former advisor's lab, I visited there more than 3 times each per year. And the box of the equipments was still unopened. Yeah, it was wasted, and I really regret uh, about my decision. At that time, I was so, how to say that, so dragged by the determinism, like, okay, I have my life plan, this, that, 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 and I will never deviate from that, something like that. And it was one of the most stupid idea. So from the beginning, I asked my sons, especially the first one, never think in that way because he so resembles me in every aspect. And as many of you have already seen from his outfit, yeah. Anyway, so this is a quite interesting idea, and so I pursued that idea. That's why I had that 2004 paper. The many contents, almost every mathematical tools I never learned before I graduate. I learned by myself. And the unfortunate part was that that was too mathematical to be applied to practical system design. So my next venture should have been directed to how can I make this more practical, more applicable to current system design? And that waited more than 2 decades, unfortunately. Anyway, so I will not cover all the parts, and uh, you may follow most of the ideas in this paper. Okay, what is the next paper? Let me show you. Yeah. And this is, by the way, the previous paper was written by myself and one of the master's course student at that time. So Dr. Yeohun Yoon, now with Samsung Networks, wrote this paper. He was a master's student, master's program student. He was one of the most hardworking RA of my lab. But actually, still, I believe the Young Yun Kang and Young Gun Yu were more diligent, hardworking students. They were really, really amazing. And this paper is written by myself and my first graduate student. He graduated in the second because the paper was once rejected. Precisely speaking, the paper was originally part 1, part 2 paper submitted to TCOM. And the reviewers rejected the part 2 and moved some of the results to this version. And something more was that one of the reviewer didn't like the proper complex Gaussian noise assumption. So Byung-Woo Khan and I redo every work again for improper complex Gaussian random processes. And we've found something very, very interesting, which was far different from the previous research results generated by the cyclostationary, the Signal Processing Society. So since this today is the first day to cover this one, let me just follow some figures. And as you see, the signal model is almost the same always. Simple. Consider you have a transmit signal, X, and you have a band-limited LTI channel, and you have ambient noise, probably Gaussian, white Gaussian noise, and you have interference modeled as a Gaussian random process. But this is not just the Gaussian random process. It is a general improper complex Gaussian random process. And given that, we view this as a channel, band-limited channel, and want to find out the capacity of this channel. That's why the paper is entitled as the capacity of second-order cyclostationary complex Gaussian channel. Precisely speaking, this is not only complex, it's improper complex. Got it? And Byung-Wook and I decided not to put improper here. We wanted to keep the original title. It was something like part 1, blah, blah, but anyway, that part is gone. And the original submission had that satellite link figure, which is totally removed from this version. So we had satellite, uplink, and downlink, and receivers, broadcasts, something like that. So this paper is really information theoretic version of 2004 paper and the previous paper, J16? We've just seen, J15, got it? So here, the performance metric was what? Mean squared error at the output of a linear receiver, subject to some interference, right? Of course, here, we have another orthogonality constraint. So precisely speaking, we are extending 2004 paper only. However, we've already knew that what? Here, legacy signal can be viewed through multi-stream decomposition, any number of signals. So what we had is that in our mind is that our capacity should not depend on our choice of cyclostationary period of interference. So interference may have cyclostationarity and period capital T. We may view that random process as summation of two cyclostationary random processes with period 2t, three random processes with cycle period 3t, right? And our capacity should not depend on that choice. And we really wanted to see whether our capacity depends on that choice or not, and the answer was obvious. It shouldn't be depending on our choice because capacity must be the ultimate performance metric. Anyway, so here, this is what AWGN probably, and this is with cycle period T. And if you read, we start from vectorizing X and Y and N's and even H of T, matrixizing, right? You know how to convert this to a MIMO system, right? In the time domain, right? You vectorize H of T and put each component in the diagonal entries of a matrix valued impulse response, right? And we compute the capacity and we choose different choice of cycle period, which means that we choose different vectorization and see whether we have the same capacity or not. That part is included somewhere. And where it is? Yeah, somewhere. I do not remember. Yes. Yeah, somewhere. Anyway. Yeah, probably here. Yeah. For some positive integer k, and probably capacity is the same regardless of your choice of k, something like that. Anyway. By the way, why we assume Gaussian noise, Gaussian interference? Otherwise, it's very, very hard to compute the capacity. Actually, it's almost impossible to compute the capacity, except that you numerically approximate the capacity. Actually, capacity can always be approximated by generating many, many, many ensembles for the input and output as far as you have the optimal input. And you use the Monte Carlo, which means you rely on law of large numbers to compute that approximate mutual information. So actually, you can do that as far as you know the optimal input distribution. The problem is that when you have non-Gaussian interference present in the channel, nobody knows what is the optimal input distribution in general. And you may say that, wait a minute, can you do it in the frequency domain? The frequency domain approach makes everything worse because as you know that, how can you distinguish BPSK signal and pi over 2 BPSK signal by just Fourier transforming the sample passes? It's not easy. I'm not saying it's impossible. It's not easy. So here, the paper has a limitation in that it assumes interference is also Gaussian. However, in order to kind of include something like PAM interference, we assumed improper Gaussian. So before I stop, let me just give you the definition for a random variable. First, So if x and y are jointly random, real random variables, then z is a complex random variable. Let me define in that way. Got it? Now, given a complex random variable, we can define the mean as usual. And we can define the variance. But here, sorry, we use magnitude square to define the variable. And this is kind of very normal. But here, some people in the signal processing and communication society wants to define so-called pseudo variance or complementary variance. That has what? Parentheses instead of magnitude square. Why? And it can be shown that you have how many correlations? Self-correlation and cross-correlation. Unfortunately, this one only gives you what? Only gives you what? If I remember correctly, this one. Okay? So no cross-correlation appears at all in the ordinary variance of a complex random variable. Got it? Because if you take the real and imaginary parts, magnitude square of a complex number is due to the Pythagorean theorem is what? Real part square plus imaginary part square. There is no cross product, cross term. So cross correlation between x and y never appears in the ordinary variance of a complex random variable. That's why people wanted to define this. Of course, you may just use the correlation between x and y. However, people wanted some artistic symmetry. That's why they have variance and complementary or pseudo variance. And what do you have now? Unlike the variance, complementary variance has what? Am I right? I believe so, right? Am I right? Now, what is a proper and improper random variable, complex random variable? So if the complementary or pseudo variance vanishes or equals 0, then the random variable is called proper or proper complex random variable. What is the consequence? So this if means if and only if. So you may say that lemma z is proper if and only if. Be careful. In the definition, you may just say if to mean if and only if. But in lemma, which is the equivalent definition of propriety, you must use if and only if. One, variance of real part must be same as variance of imaginary part. Second, covariance must be 0. Got it? And z is called improper otherwise. So this new definition of complementary variance or propriety divides the entire set of complex random variables into two: proper complex random variables and improper complex random variables. Got it? However, you may just see proper random variable as a special case. You may view proper random variable as a special case of a random variable that has vanishing pseudo variance. So just starting with possibly non-zero complementary variance from the beginning and derive all the results and plug in zero or non-zero may suffice for the complete derivation of the result that covers proper and improper cases, all of the cases, right? So from now on, whenever you see a complex valued random variable, remember that you have to handle both of the variances. And this extends to what? Not only complex random variables, complex random vectors, complex random processes, and complex vector valued random processes. Got it? And many of you already know that sometimes your time varying channel is modeled as a complex Gaussian random field. In that case, you can assume this complex Gaussian random field is proper or sometimes improper, depending on your channel model. Got it? So this proper improperness or propriety or impropriety applies to every complex valued something with uncertainty. It could be scalar, vector, even matrix, if you want, field, anything. Got it? So be careful. Ordinary variance, just using the magnitude square, is not enough. If you use only that one, you lose information in the cross correlation. Okay, that's all for the day.